and we ask if we can dilate that. So this has got a tool that just dilates. So I'm going to take that shape and I'm going to dilate it around 0, 0. That's going to be the easiest thing to do. And we'll spend a lot of time in chapter 9 actually physically doing this stuff. But what I want you to understand with that chapter is that it's using principles that this chapter discusses. I'm going to take that shape. I don't know why 0, 0 disappeared. Sorry. 0, 0. There we go. What in the heck? All right. Take that shape, dilate it there. Let's say I want a scale factor of 3. So it makes a shape that all side lengths are 3 times as big. Does that make sense? Okay. Now what happens here is, so let's say this was the shape that I enlarged by a factor of 3. What happens is if I move this to where point D actually lands on the origin, do you see there that these angles here kind of matched up, or those of the small shape and the big shape? I should be able to do that with every angle. So let's try to get point C on E. And those angles matched up. The same thing with B, and those angles match up, right? Does that kind of make sense? So this was a feature, and I don't know how much you would have spent time in like 7th, 8th grade actually recognizing that feature. But what happens is that when you dilate something, the angles stay congruent. Does that make sense? Now the side lengths are different, okay? And they're different by a multiple of 3. But when we do a dilation, the resulting images, the image and the pre-image, are what we call similar shapes. Okay? So what I'm trying to get at here and kind of discuss a little bit with you is what we talked about today. You've had these shapes in front of you before. Whether you talked about them in this concept and in regards to similarity or not, I'm not sure. Okay? But you have dealt in some aspects with similar shapes. Does that make sense? So our definition, if you remember what it meant for things to be congruent, I'll write this definition up here. You don't have to write this, but congruent, the definition we introduced there was same shape, same size. When we talk about similar is going to be the same shape. So a quadrilateral can only be similar to a quadrilateral. A triangle can only be similar to a triangle. A circle to a circle. We can actually work with things that are not polygons. So same shape but different sizes, okay, is usually what we attribute to a similar relationship, okay? And what that does then, when we look at this definition, of saying same shape, different size, the fact that they're the same shape means that this condition number 1 down here has to be met. Okay, when you have two shapes that are the same shape, we are arguing then that the corresponding or matching angles are congruent. Kind of like I just showed you by overlapping those two images, right? Okay. The other thing that happens, and this is where 7.1 kind of kicks in, and the purpose of 7.1 is that corresponding sides are in proportion. Corresponding sides are in proportion, meaning that when I compare multiple sets of corresponding sides, they should set up a proportion to one another. Okay, a true proportion. Okay, sometimes we say that they're in the same ratio as one another or something like that. Meaning that if I compare in this graphic here, if I compare corresponding sides, let's say AD is 10, right? Okay. Now AD, the reason I'm going to correspond AD, that segment to EH, is not because they're both the top segments. Okay. I'm going to learn that I'm going to correspond those because AD, the angles are a 1 marking and a 4 marking, right? That makes sense for the angles and how we identify them? And then I look at E and H. E has 1 mark in it and H has 4 marks in it. Okay? If you start doing that comparison, you guys have demonstrated that you did that with congruency pretty effectively. You are going to set yourself up for success with these. The people that mess these up and struggle with similarity always compare like top to top, bottom to bottom, left to left, right to right. Okay? And you can do that essentially in this problem, but it's because those two shapes are in the same orientation to one another. Does that make sense? That the one on the right could be rotated, could be flipped, could be inverted, whatever. But right now they're not. It's just like a cut and paste and we shrink it. Okay? So left and left, right and right, bottom and bottom does make sense here, but I don't want you to learn it that way for when maybe I do something like this. Let's say I take this shape, paste it, and now I think I can do a, see where it says flip anywhere? There you go, flip horizontally. Now if I did top to top matches, right? Bottom to bottom still match, but does left to left match and right to right match? Does that kind of make sense to everybody? Okay, so just be on the lookout. You don't know how that shape can rotate, flip itself, reflect itself is the math word. So just be on the lookout for that. But I'm going to go by the markings and the angle. So 10 compares to 5. Okay, if I look at this, so this has 4 marks in it, angle D has 4 marks in it, angle C has 3. Over here, H has 4, G has 3, so I should be able to say 8 compares to 4. The bottom, C to B, that's 3 to 2. Over here, it's 3 to 2. So I'm going to say 6 compares to 3. And I think, because the last ones are obviously going to have to match up then, 5 is going to compare to 2.5. This argument right here that says the corresponding sides are in proportion must mean then that I should be able to take any two of those ratios, any two of them, and get a true proportion. So if I take those two right there, is that a true proportion? How do I check that? Cross multiply. If I cross multiply, do I get 40 equals 40? So that's a true proportion. That's a true statement right there. Okay? Now I should also be able to maybe take that one equal to that one. If I cross multiply those, what do I get? 30 equals 30, right? Still a true statement. It's not the same 40, but I don't care about that. I just care that I get something that is equal. 30 equals 30. So those two are an equal proportion or true proportion. What about like those two? 24 equals 24, right? We're good there. What about these two? 15 equals 15? And if we understand our transitive properties, we should be able to link, if I can say that those two are true, say that these two are true, and say that then these two are true, 8/4 and 6/3 kind of links the boxes, right? Does that kind of make sense? So then that means to me that I should be able, if those are all true from that individual blue box, purple box, red box, then we should be able to take any two of those, maybe the first one in the blue box and the last one in the red box, and use the transitive property to say 10/5 is going to equal 5 over 2.5. And cross multiply those, I get 25 equals 25 anyways, right? Kind of make sense? Okay. But that's the idea of statement 2 there. It says corresponding sides are in proportion. Now some people are going to argue that, well, why are you doing that? Why are you going ahead and cross multiplying where we obviously know that 10/5 is 2 over 1, right? We know 8/4 is 2 over 1. We know 6/3 is 2 over 1. We get to this fraction, it's not as nice and convenient as the other ones, but we know 5 and 2.5 are in a 2-to-1 relationship, right? So if they all corresponding sets of sides reduce to the same number, then they're proportional. Does that make sense? Okay. Sometimes that number will be a whole number like 2. Other times it might be a nasty decimal. We'll see an example here towards the end where that number is irrational. Okay. But it's still the same number each time. So that's what we mean by similar. Same shape, different sizes. And what we're going to pretty much focus on is working with the side lengths and working with what that proportion aspect of the shapes is going to kind of lend us to be able to do some shapes. Don't write this, but it says when talking about two figures being similar, we make similarity statements much like we make congruency statements. Okay? Remember, if I had a triangle ABC, we'll say triangle ABC is congruent to triangle XYZ. The way we named that told you how A related to X, right? It told you how B relates to Y and how C relates to Z, right? You remember that? Okay, and we can do the same thing with segments. We end up with congruencies with segments as well. The same thing exists when we talk about similarity, okay? We need to understand that the order cannot just be haphazard when you name them, okay? There has to be a process for naming these things. First thing I want to talk about first, the shapes here I'm dealing with are both quadrilaterals, four points here. This symbol right here, okay, your tilde, I don't know if that's how you spell it, but that is your, in mathematics, that's your similarity statement, okay, or your similarity symbol, okay. So the way we read that is we say ABCD is similar to EFGH. ABCD is similar to EFGH. So we're going to draw a little sketch here. If you ever worked in like edited photos and stuff like that, you guys crop pictures, right? Copy pictures, and when you copy those pictures, you then might want to resize them, right? And when you resize them, okay, as long as you keep the aspect ratio the same, meaning that however I change the horizontal distance, I change the vertical distance the same way, your images are just going to be enlarged and they're not going to be distorted, right? Does that make sense? Okay. To where if I would have done, I think I can do it, maybe. Let's go back to this. If I would have done this, that distorts it. Does that make sense? So that means I made the vertical compressed, but I didn't do anything to the horizontal. So that's not a similar shape. But if I attack that corner that way, now they're similar. Okay, because I changed the X the same way I changed the Y. I'm going to rename this. When I did that, my computer is actually using this geometry that we're talking about. I'm going to name this point E. I'm going to name this one F. I'm going to name this one G. And I'm going to name this one H. Because my argument then is going to be that if I take, get back to selecting that little small one. Well, get this way. There you go. If I take that small one and I move it so that A and E lay on top of each other, do they still end up being congruent? Does that make sense? Are D and H congruent? Okay. Are B and F congruent? And I think you guys can, I'm not going to scroll up there, but I think you could probably argue that those two, C and G have to be congruent. Okay. So what I want you to know is that I really don't need the picture to be able to argue that. Okay. As long as I have this similarity statement, A is congruent to E. The first two letters, just like when we talk about congruencies with polygons and congruency statements, the angles as individual letters match up and should be congruent. So angle A is congruent to angle E, angle B is congruent to angle F, angle C is congruent to angle G, and angle D is congruent to angle H. Is that okay? So the angles match up and should be congruent. Now, what is a little bit different than what we talked about with congruencies, when I put that that quadrilateral on top of this one, obviously those side lengths are not the same. Okay, so if I take, I don't know where it's pasting it. If I take that one there and put it there, obviously A to B is not the same thing as E to F, right? A to B is not the same thing as E to F. E to H is not the same thing as A to D, okay? However, when I do this, when I compare this segment here, A to B, to that segment there, whatever that ratio is, should be identical to that ratio. Does that make sense? Which should be identical to that ratio. All right. So what I'm trying to get at here is that when we look at our similarity statements, when we talk about the angles, we can say the angles are congruent. But when we talk about the segments, we talk about how they relate to one another as ratios. So the first two letters, and this is the same way we kind of pick them off in congruencies. You take the first two letters here, and that's a segment, right? You take the first two letters over here, and that's another segment. And they should correspond. But look what we do down here. That means that the ratio, whatever that ratio turns out to be, is then going to be the same thing as if I take the next two letters BC and the next two letters FG, and I compare them in a ratio. Whatever that fraction is in blue is going to be identical to that fraction in green. Okay? And then the next two letters are CD in the figure on the left compared to GH on the figure on the right. And that ratio should be the same. And I keep doing that, corresponding segments all the way around until I write or exhaust all my different ratios. Okay? Now, what we're saying there, that's an extended proportion, right? In 7.1, we talked about extended proportions. And what we talked about is that you should, because these are all equal, you should be able to take this one and set it equal to any of these three, and you're fine. You're going to get a true statement. I should be able to take that one and set it equal to any of those three, and it should be true. I can do that with all of them. Does that make sense? Okay? And that's going to be the tool that we use to do some of these algebraic problems that we're going to see later on. I'll skip that for now. We'll do this. We'll kind of talk about how we can use this in a specific problem. Now, early on, I'm going to draw my pictures. This won't be the case in your homework all the time. But I'm going to try to draw my pictures so that they're in the same orientation to one another. Okay? I want to make sure that we don't make the argument that these two things get compared, because I can go bottom compared to bottom, left compared to left, upper left, upper right to upper right, and lower right to lower right in regards to their segments, and say that always works. Does that make sense? Okay. I don't want to say that, you know, the top angle is Y and the top angle is B. Well, it's because they're both top angles, they have to be congruent. Or that's not how it works. Okay. I'm going to give you the congruency statement here. I'm going to say that VWXYZ, I guess the similarity statement, I apologize, similarity statement is the same as DEABC. Okay. So what they're saying here then is that VW, which is the first two letters here, compares to DE, which are the first two letters there, right? So if I write that arbitrary statement, VW compares to DE, I can then look at my picture and say, well, VW is 21 and DE is 35, right? Do those have a common factor in them? What do they both divide by? 7. So I get 3/5 here, right? This number 3/5 is called your scale factor. Okay, if you go back to dilations, you might have in 7th or 8th grade, there's a couple different ways textbooks talk about it. They could have called it a scale factor. They could have called it a dilation factor. They might, if you're doing an enlargement, they could have called it your enlargement factor or a reduction factor. Okay, those are kind of the terms that we use. In this class, we're going to use scale factor because that kind of encompasses all those kind of synonyms. Okay, that's our scale factor, and that number tells me how I can take 21 and make it 35, or how I can take 35 and make it 21. Does that make sense? Okay. It shows me how we can enlarge or reduce one of these shapes because they're similar. So that tells me that there is an enlargement or reduction taking place here. That 3/5 is the idea that if I look at VW compared to DE, I look at WX compared to EA, and I look at XY compared to AB and the other ones as well. When I have actual values for VW and DE, it's going to go to 3/5. When I have actual values for WX and EA, it's going to divide it by 3/5. When I have actual values for XY and AB, they're going to divide by 3/5. Does that make sense? The scale factor is that when I look at the individual ratios in my similarity statement, it is that value for those individual ratios. Okay? We can use that to our benefit. What they're going to do a lot of times is they're going to ask you, if you know that YZ is 15, can you find BC's length? Okay? Now here's my question to you. And it's depending on how you want to start this, but I'm going to start here at 21. And I know 21 has grown to 35. Does that make sense? If I'm going to take 21, and just to go back to some algebra concepts here, and I'm going to multiply 21 by something to make it bigger, like 35, what kind of number do you have to multiply 21 by, or any number, to enlarge it? If I multiply by 1, does it do anything to it? So that's kind of my break-even point. That's where I stay static by multiplying something by 1. If I multiply 21 by 2, does that enlarge it? If I multiply by 3, does that enlarge it? If I multiply by 1.5, does that enlarge it? If I multiply 21 by a half, what does that do? Reduces it, right? Cuts it in half. Divides it by 2, essentially. Okay? If I multiply it by a fourth, it's going to cut it into fourths. Okay? So when I want to multiply 21 and make it go to 35, I need to know that I need to multiply it by a number bigger than 1. Does that make sense? Well, if I just said my scale factor is 3/5, that's the tool that I'm going to use. That's what I'm going to multiply by. If I multiply by 3/5, what's that going to do to 21? It's going to shrink it. It's going to reduce it. So what should I multiply by instead? Multiply by 5/3, right? The reciprocal. Does that make sense, everybody? 21 times 5/3. 5/3 is bigger than 1. 21 over 1 times 5/3. The 3 and the 21 cancel. The 7 times 5, give me that 35. So if these two shapes are similar, I should be able to do the same thing with that 15 to turn it into that x. Take 15. Do this aside here, a little bit more room. We'll take 15 and multiply it by 5/3, and that should give me x. 15 times 5 is 75. 1 times 3 is 3. And I get that. Okay? And now the reason that's not the way I'm going to do any problem ever again with you guys. The reason I show it that way is because a lot of people do that and say, Faye, what you do in class is not what I do. Because I don't understand the way you do it in class, or I'm doing it this way and it's different. What I want to kind of explain right now is that you might be a person that eventually does a problem differently than what I do, but I want to argue to you that it's not different. Okay? And here's why. I'm always going to say, when I do this process, I want you to learn to deal with similarity the way the definition sets up similarity. Okay? So that you always have a way to get the answer correct. Okay? So this is what I do. I always say, okay, so 21 compared to 35. Okay? I'm going to set up a proportion. So 21 went to 35. Okay? If you remember when we talked about setting up proportions, we like our numerators to have something in common. Okay? In all these polygon questions, my numerators are going to come from the same shape. So I always keep my numerators the small shape. So 21 came from the small shape. 15 comes from the small shape, right? What did 35 come from? Big shape, right? So does x come from the big shape? So across the numerators, those are similar, or those are the coming from the same shape. Denominator coming from the same shape. If I look at those as a group, 21 compared to 35, well, those are corresponding parts, right? Those are the relationships from one shape to the next, but they are matching parts, okay? 15 over x, those are matching parts. Does that make sense to everybody? Okay, so that's the way I'm going to set this up. Now that's a proportion, right? Okay, now I don't like 21 over 35, so I don't want to do that math. I'm going to write this as 3 over 5 now equals 15 over x, right? And what do we do when we want to solve a proportion? Cross multiply. Is this the same thing that we were doing here? Do I get 75 and divide it by 3 at some point? Okay, so divide both sides by 3 here, I get x to be 25. Okay, now I know that you might be still saying, well, it doesn't look like the same exact algebra. Let me do this. If I have that proportion, are you allowed to find the reciprocal of both sides and get that proportion? That makes sense? Okay. Now, algebraically from, Mr. McCoy, Mr. Herb, Mrs. Coles last year, you were taught that this is a rational equation and you can multiply by an LCD, right? You don't have to cross multiply. You can multiply by the value that you can make the smallest value that you can make both these denominators turn into through multiplication. That's what the LCD is. That's 15. Multiply this side by 15. Multiply this side by 15. When I do that, it leaves me just x on the right, correct? Is this exactly right there what I wrote up here? That makes sense, everybody? So my argument is that if you're a person that goes this first route, that's fine, it works. And by all means, use it. That's fine, if that makes sense to you. Okay? I think logically arguing how to do that can be problematic for some people. So I'm going to use the definition of similarity. But I want you to know that we're doing the same thing. Okay? It's just kind of manipulating the algebra a little bit differently. Important person today. All right, let's go to, you don't have to write this down. This just talks about how when we compare things, it's going to be important how we do that, okay? When we're talking about scale factors, and my scale factor, for instance, of A, B, C, D to E, F, G, H here is 2, that is different than saying that the scale factor E, F, G, H to A, B, C, D is 1/2. Okay, that's very important that we understand that. There's going to be quite a few homework questions, test questions, quiz questions that ask you for a scale factor. In the past, people would write, oh, I wrote down 3/5, but it was 5/3. Well, that's a problem, because then if you're going to use that 3/5 or 5/3 appropriately, and you have it as the incorrect one, okay, you're going to enlarge or reduce inappropriately. Does that make sense? Okay, if my scale factor is 3 to 5, and I want to use that to reduce something, but I use 5/3, I've actually enlarged it instead of reduced, right? So that's the importance of knowing how we should be comparing things. Order matters, okay? Order matters. Don't write this either. I think we've talked about this several times. I don't know if we formally defined it, but when talking about similarity, a lot of times the authors, the textbooks, the problems in Math Excel, they don't use like A, B, C, D, and then go on to E, F, G, H. They'll say A, and if they want to use A again, we'll use A prime. Now, the reason we do that, if you're going to use this technique, then make sure that A and A prime are the angles that match up. Does that make sense? Okay. It would not make sense to put like A prime up there, because when you use this notation, the collected math community makes the assumption that whenever they see A and A prime in text, that there's a relationship between them. Well, if I put A prime up here, there's no relationship between that angle and that angle. Does that make sense? So what we would do here is we would say this similarity statement. And what that allows then is just to say, okay, well, I know AB is going to match up to A prime, B prime, and it's just really easy to write that ratio. Does that make sense? Okay, so just some notation stuff. This is the nuts and bolts of it. This is why we do this type of thing. You're going to see a lot of questions in your homework like this. The end of course exam is always going to put one of these on there. They're going to ask you to find X, Y, and Z. What I would be cautious of, and this is the way I do all these problems, I said this at the beginning of the year with Math Excel, don't try to pigeonhole yourself into finding X first, and then pigeonhole yourself into finding Y and then Z because they're alphabetical. Write down what we know. Do the whole problem, and then once you have all your answers, then go plug them into Math Excel however they want them, okay? So here's what I like to argue. If I know this is quadrilateral ABCD, similar to quadrilateral A prime, B prime, C prime, D prime, you know then automatically, because they're similar, that this should be true. Okay, that's exactly what our definition of similarity tells us in a similarity statement, right? Corresponding sides should be proportional. Okay. Now you could have looked at the reciprocals of all those two. You want to put the A prime, B prime on top, the B prime, C prime on top, so forth. You can, doesn't matter. Now what I'm going to do is, because now I know how these sides are supposed to relate to one another, and this is very beneficial if these shapes were like this. Rotate. So let's say our shapes were like that, and obviously not the same orientation, right? Okay. It is going to be so much easier to look at the similarity statement instead of trying to say, okay, that segment right there, which one over here does it match up to? That one. It's a lot easier to say, okay, AB, yep, A prime, B prime. So now I come over here, find A prime, B prime. No, it matches up to Z. Does that make sense? So that's the purpose of why I show it this way here. Okay. Now I should go in and plug in what those values are. AB was 10. A prime, B prime is Z. BC is 20. B prime, C prime is 30. CD was 8. C prime, D prime is Y. DA, X, D prime, A prime, 21. Is it okay with everyone? Now if I look at those, if these two shapes were similar, which that's what they said at the beginning, they are, I don't know what this ratio here is. Z is unknown. I don't know what that ratio is because Y is unknown. I don't know what that ratio is because X is unknown. And all the problems that you work through, one of them will be known. 20 over 30. Okay? What's that reduced to? 2/3. 2/3 is my scale factor. That's what that means. Okay? That means then that 10 over Z, whatever Z is, 10 over that needs to divide to give me 2/3. Does that make sense? So what I like to do is like, okay, now I'm just gonna set this up, say 10 over Z equals 2/3, and I should be able to solve that. 2Z equals 30, right? Z 15. Okay. Then I'm going to take this 2/3 and I'm going to set it equal to another one of these. Maybe I'll take those two. So 2/3 equals 8 over Y. So give me 2Y equals 24. So then Y is 12. And then the last one, 2/3 compares to X over 21. 3X is going to equal 21 times 2. So that's going to be 7 times 2, which is 14. Does that kind of make sense? If you set up those four ratios, you know it's an extended proportion. They're all equal. You can grab any two that you want to, and then cross multiply to solve for X, Y, and Z as you see fit. Does that make sense? Okay. Now I want to show you the next question is find these perimeters. I don't know how often they ask you to do this. This will be it's usually a question on the end of course exam, a relationship that they are interested in. If this is 14, Z we said was 15 and Y was 12. So we add these together, so this is going to be 30, 44 plus 8, 52, right? The perimeter of that small one is 52. When I look at the big one, 45 plus this, so that's 57, 58, 78, 52 to 78. Okay, so it's nice. Okay, but let's kind of mess around with that a little bit more. What do they both divide by? Both even, right? Both divide by 2? All right, that way? Does anybody see another number that they both divide by? Say it again. 3.
Is it 13?
Say it again.
13.
13. 39 divides by 3. It gives me 13, but this one doesn't divide by 3. But they both do divide by 13. 26 divided by 13 is 2, right? 39 divided by 13 is 3. What was that number? 2 to 3? It was your scale factor. Okay? So and this is just one example, but that's a theorem. Okay, your scale factor is equal to the ratio of perimeters. So sometimes they'll ask you questions to where maybe they don't give you enough information. So maybe we just go back to like looking at just this picture, but I don't give you 10, x, 8, or 15, 21, or y. I don't give you any of those. I just give you the 20 over 30. Okay? 20 compares to 30. I know these two shapes are similar, and I'll ask you, if you know these two shapes are similar and you see that 20 compares to 30, what's the scale factor? We'll say 2/3, and I'll ask you, okay, what's the comparison or the ratio of the perimeters? Well, because I didn't give you the other sides, you have no way of finding what the perimeters are total, right? But this theorem allows you to at least know how they compare. They're 2 to 3, okay? And we'll talk. It's an easy theorem to prove. If we have a little bit of time tomorrow, I'll show you that algebra. But it's ultimately because of a 2/3 being in. This multiplied by 2/3 gives me that. 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 So then that 2/3 can actually be factored out, and we get the comparison of perimeters that way. So we'll talk about that tomorrow. I'll open up 7.2. You're going to see a couple questions like this. Just pay attention. Be on the lookout, because I think sometimes they train you not on purpose to compare things left to left, top to top, bottom to bottom, right to right. And you get in the habit of doing that because it's working. And then they flip a picture, or they rotate it, or whatever, and you try to use that, and it gets you the wrong answer. So make sure that you're using this tool here with the similarity statement to help create your algebra.